My name is Enrichment, and in this video I will present 26 key concepts of chemistry corresponding with the 26 letters of the alphabet. I plan to spend around 20 to 25 seconds on each letter, presenting first a definition, then giving a generalized overview, and then explaining how this concept is used in chemistry. I'll cover foundational concepts as well as specific concepts that I find personally interesting. The first letter of the alphabet is A, and that corresponds to atom. Atom is the defining unit of an element, which cannot be subdivided using chemical means. It consists of three subatomic particles. First, we have the proton, which carries a positive charge, the neutrons, which have a neutral charge, and electrons, which have a negative charge. Now, how is this concept used in chemistry? Well, atoms provide the basis for the chemical world. All elements consist of atoms with different numbers of protons, which will indicate their atomic number. Atoms are combined to create molecules, all of which have different properties and roles in the natural world. Next up is B, which stands for beta decay. Beta decay is defined as the type of radioactive decay that results in spontaneous emission of a beta particle. Now, what is this beta particle, you may ask? Well, a beta particle is basically an electron. It carries a negligible mass, but a negative charge. Here's an example of beta decay where you can see the beta molecule. How is this concept used in chemistry? Well, it allows for unstable radioactive isotopes of elements to stabilize. Also, beta radiation poses health risks such as burns and life, but it can also be used as a treatment for cancer in the medical field. C is for carbon. Carbon is defined as the chemical element with atomic number 6. It has 6 protons, which would be its atomic number, and is located in group 4. It is also a non-metal. Now, how is carbon used in chemistry? Well, all living things contain carbon. It's the basic building block of life. Virtually all molecules in the human body contain carbon, for example. Carbon has the ability to bond to 4 groups around it. It has a possibility of long chains with varying properties, which gives this molecule the basis for organic chemistry. It corresponds with de Broglie's equation. It's defined as an equation describing the wavelength properties of matter, and it is stated as wavelength is equal to Planck's constant divided by mass times volume, where mass is measured in kilograms and velocity is measured in meters per second. Now, an increase in mass or velocity would indicate a decreased wavelength and also an increase in energy. Now, how is this concept used in chemistry? Well, de Broglie hypothesized that light behaves as both a particle and a wave. His equation declares that every moving particle, regardless of size, is associated with a wavelength, whether that's a molecule or a baseball. It stands for element. An element is defined as a substance that cannot be subdivided using chemical means. It's identified by the number of protons in its atoms or the atomic number. Now, how is an element used in chemistry? Well, there's 118 known elements that form life as we know it. Each of these elements have different properties, such as heat capacity, electronegativity, and atomic mass. Now, these elements form the building block of life-sustaining molecular compounds such as water, so they are very useful in life. Which stands for fusion. Fusion is combining light atomic nuclei to form heavier nuclei, and this is accompanied by the release of energy. Now, how is fusion used in chemistry? Well, all elements with an atomic number less than irons formed through nuclear fusion occurring in stars. Now, after the Big Bang, hydrogen fuses with hydrogen stars to form helium, and this occurs for every single element, and so on. Now, it's essential in the formation of new elements. G stands for gamma radiation. Gamma radiation is defined as the high-energy ionizing photons originating from the atomic nucleus. Now, gamma radiation waves have the smallest wavelength and therefore the highest energy. We can think back to the de Broglie equation for that. And that's of any wave in the electromagnetic spectrum. It's often represented by the gamma Greek symbol, right here. It has a high penetrating power, no mass, and a neutral charge. Now, how is this concept used in chemistry? Well, in the medical world, for example, gamma rays are used to kill cancerous cells. H is for halogen. A halogen is defined as an element in group 7 of the periodic table. Example halogens would be chlorine, fluorine, and bromine. Now, these are all nonmetals. How is the concept used in chemistry? Well, halogens rarely form bonds with other molecules, and this is because they all have 7 valence electrons, and they want to fulfill their valence shell with 8 electrons according to the octet rule. Next up is I, which stands for isotope. Isotopes are defined as atoms that have the same number of protons, but different numbers of neutrons and thus different atomic weights. For example, we have carbon-12, which is the natural isotope. We also have carbon-13 and carbon-14, which are other isotopes that are radioactive. Now, how is this concept used in chemistry? Well, elements have a variety of isotopes, where the sum of the isotopes' masses times the frequency in nature is equal to the average atomic mass. Now, radioactive isotopes experience radioactive decay in order to become the natural isotope, where they're most stable. Joule. And joule is defined as the SI unit of energy equal to the kinetic energy of 1 kilogram mass times meter squared over second squared. How is this concept used in chemistry? Well, joule, which is defined by the J, is used to express the amount of energy in equations such as the de Broglie equation, and it's an essential quantitative measurement for energy. Which is the Kelvin temperature scale. The Kelvin temperature scale is defined as an absolute temperature scale of 100 degrees between the freezing and boiling points of water, although values are given without degrees by convention. Now, when we're converting from degrees Celsius to Kelvin, which is degrees Celsius is a popular temperature scale, we have Kelvin is equal to degrees Celsius plus 273.15 Kelvin. Now, how is this concept used in chemistry? Well, the Kelvin temperature scale provides a standardized measurement of temperature in the scientific world. L, which is Lewis-dot structures. Now, the Lewis-dot structure defines the representation of a molecule that uses dots to show electrons around atoms and lines to show covalent bonds. Now, in the compound hydrogen bromide, for example, we have a line that indicates the sharing of electrons or a covalent bond. How is this concept used in chemistry? Well, it indicates a visual illustration of the valence electrons of an element and also the sharing of valence electrons in covalent bonds. Per mole. The mole is the chemical mass unit equal to 6.022 times 10 to the 23 objects. And this 6.022 times 10 to the 23 objects is known as Avogadro's number. And the objects could be particles or molecules or atoms. How is this concept used in chemistry? Well, the mole provides a standardized amount that allows for mole conversions, such as in stoichiometry. An example would be going from grams of one substance, then you go to the moles, and then you go to the number of particles in that same substance. N is for nucleus. The nucleus is the positively charged center of an atom, made from protons and neutrons. Now, a fun fact about the nucleus is that nearly all of the mass of the atom is found in the nucleus, yet the nucleus itself is much smaller than the overall diameter of the atom. Now, how is this concept used in chemistry? Well, the nucleus contains a concentration of protons which carry a positive charge, and these attract electrons. Next up is O, which stands for octet rule. The definition of the octet rule is that it is the principle that bonded atoms share their 8 outer electrons. This gives the atom a valence shell resembling that of a noble gas, of which it is most stable. Now, how is this concept used in chemistry? Well, the octet rule provides the basis for the theory behind bonded atoms. So in ionic bonding, for example, electrons are donated or accepted to satisfy the octet rule. So sodium forms a cation when it bonds with chlorine, which forms an anion. After the transfer of electrons, both atoms satisfy the octet rule and are most stable. Next up is P, which stands for phase diagram. The definition of a phase diagram is that it is a chart portraying the thermodynamic conditions of a substance at different pressures and temperatures. So for example, you can see a phase diagram here, where this line right here between the solid and liquid phases marks the transition of a substance from solid to liquid at this specific pressure and temperature. The triple point is the point at which the solids and liquids and gases all exist at equilibrium. Next up is Q, which stands for quantum numbers. The definition of a quantum number is that it is a value that is used when describing the energy levels available to atoms and molecules. How is this concept used in chemistry? Well, electron states are described by 4 quantum numbers, as you can see here. These numbers are used to calculate the electron configuration of an atom, which is used to determine the valence electrons of an atom, and also to determine the probable location of an electron at a given point in time. R is for resonance, which is a method of describing the delocalized electrons in some molecules where the bonding cannot be explicitly expressed by a single Lewis structure, such as in carbonate. Now, how is this concept used in chemistry? Well, sometimes molecules cannot be described explicitly by a single Lewis structure, so you have to have molecules where the valence electrons move to stabilize the molecule. So each structure has the same number of electrons, but they are positioned differently, symbolized by these double bonds moving. Next up is S, which stands for solubility. Solubility is the maximum quantity of a substance that may be dissolved in another. The measure of solubility determines how substances dissolve in one another. One key concept to keep straight in your head is like dissolves like. So for example, polar molecules dissolve polar molecules. This concept used in chemistry? Well, it's very important in the medical field, especially pharmacology. You need the drug to be in the form of the solution at the specific spot of absorption. So this is where like dissolves like becomes crucial. So drugs can be manipulated to reach better solubility. For example, at the molecular site. Smaller molecules dissolve faster because more surface area is available for the solvent molecules. Next up is T, which stands for theoretical yield. The definition of the theoretical yield is that it is the quantity of a product obtained from the complete conversion of the limiting reactant in a chemical reaction. Now, how is this concept used in chemistry? Well, in a laboratory setting, the actual yield will differ from the theoretical yield as a result of error. And this can be used to calculate the percent yield, which is the actual yield divided by the theoretical yield times 100%, which stands for the universal gas constant. That is the physical constant in the equation for the ideal gas law. Pressure times volume is equal to moles times the constant itself times temperature. PV is equal to nRT. Now, the value of R depends on the units for pressure, volume, and temperature. So, for example, when the pressure is in atmospheres, R is going to be about 0.08206. Now, how is this concept used in chemistry? Well, R is applicable to all gases in the ideal gas law. So this standardizes this extremely important formula, which is widely used in chemistry. Next up is V, which stands for van der Waals forces. These are the weak forces which contribute to intermolecular bonding between molecules. We have three main types: hydrogen bonding, dipole-dipole, and London dispersion. These are the weakest intermolecular forces, but they still play an important role in the properties of molecules. Now, how is this concept used in chemistry? Well, like I said before, van der Waals forces play a large role in the properties of molecules, especially in boiling point. An increase in van der Waals forces will result in an increase in the boiling point. Next up is W, which stands for wavelength. The wavelength is a property of a wave that is the distance between identical points between two successive waves. The distance between one crest to the other crest is the wavelength, which is symbolized in this image here. Now, how is this concept used in chemistry? Well, an increased wavelength results in a decreased frequency. So rays with longer wavelengths, such as radio waves, have a lower frequency than rays with shorter wavelengths, such as gamma rays. Rays with very short wavelengths can penetrate human skin and be dangerous. Extra precautions, such as a lead barrier, may be necessary in a chemical laboratory environment. X, which stands for X-rays. X-rays are light rays with a wavelength from about 0.01 to 1.0 nanometers. This is a relatively short wavelength, which would result in a high frequency and a high energy. Now, how is this concept used in chemistry? Well, it's commonly used in imaging testing, especially in the medical field. These waves penetrate the skin and other soft tissues, but are absorbed by bones, which appear on the screen. And X-rays empower doctors to view the insides of the human body without making an incision. This is especially helpful to diagnose fractured bones, as the fractures appear clearly in X-ray imaging. Y, which stands for ytterbium. Ytterbium is element number 70 with element symbol YB. Now, how is this used in chemistry? Well, ytterbium is the most commonly mispronounced and misspelled element in the periodic table. So students pursuing the chemical field must take extra precautions when spelling and pronouncing this element, as to not embarrass themselves in front of their peers. Is for ZF, which stands for effective nuclear charge. The effective nuclear charge is the net charge an electron experiences in an atom with multiple electrons. The formula, effective nuclear charge is equal to the total number of electrons, or the atomic number Z, minus the number of shielded electrons, S, is used widely in chemistry. Now, how is this concept used in chemistry? Well, ZF represents the total attractive forces that the valence electrons in a single atom have to the nucleus of an atom. So therefore, a high effective nuclear charge will result in an anion, and a low effective nuclear charge will result in a cation. Thank you for watching, and I hope you learned something.